Here today. So once again, thank you for joining. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. Today, our webinar titled The Role of Thermal Conductivity in Solid-State Hydrogen Storage. I'll be joined by a few speakers here. My colleague, Dr. Genesis Infante, from our C-Therm team, will be presenting some data. And I'm also very excited to announce Dr. Jacques Huot from the University Quebec Trois-Rivières will also be speaking in today's session. So before I pass it off to our other speakers here, just wanted to run through just a quick introduction to C-Therm, a little bit about who we are and what we do. So C-Therm Technologies, we are really experts in thermal conductivity, specifically in the transient methods space. So today's session will be heavily focused, of course, around a couple of these methods, but really our goal is to simplify thermal conductivity testing for the materials of tomorrow. And as I mentioned, we do this through the advancement of transient methods. So our Trident platform, you can see on screen here, this is our flagship product. It's one instrument with multiple methods available for thermal conductivity characterization. You can see there's 4 listed on screen there. The Flex transient plane source, the transient line source needle probe sensor, modified transient plane source MTPS, and then finally the transient hot wire THW. So in today's session, we'll be looking at a couple of these as they relate to the application of metal hydrides and hydrogen storage thermal conductivity testing. But of course, if you had any general questions about any of the methods, please feel free again to make use of that Q&A feature. And, you know, this quote here, it's one we like to use. It really embodies the idea behind Trident. It's a famous quote from Abraham Maslow: when all you have is a hammer, everything looks like a nail. One of the biggest, I'd say, issues we see with groups that are looking to test their materials is using a technique that might be really good in one area of application or for one sample type, but not so much for another. If you're, trying to force a method on a sample it just really wasn't designed for, you're setting yourself up for failure in collecting data for that material. So again, with Trident, the idea is you have more of this toolbox approach, so you can pick and choose the best option for the task at hand. Now, if you were maybe new to thermal conductivity, or just, again, maybe looking for some general information on what options exist out there, the ones that we offer as well as others available in industry, we do have this method selection guide available as a free resource download on our website. Great little resource if you are looking to just kind of understand, again, maybe some of the basics behind the transient options that we have and learn a little bit more about thermal conductivity in general. I will just mention here as well, so today's webinar is focused on core C-Therm products. But we are also partnered with both Rigaku as well as Metrovib for their line of thermal analysis as well as DMA options. So again, if you're looking at thermal conductivity and some other related properties, other thermal properties, mechanical properties, these are certainly areas where we could provide some support. And then lastly, our thermal analysis labs, TAL. A lot of groups that we work with, maybe you're not at the point where you're looking to bring something in-house, but if you're looking for options in terms of contract testing, our TAL division offers all of the Trident methods that we have available, as well as other options available in industry as well. So definitely feel free to reach out if you have any either capital equipment interests or testing needs. And the last slide here before I hand it over to Dr. Huot is just a little client testimonial. We always like to, put one of these up in the webinars just to kind of share what our users are saying about us and how they're getting along with our instruments or services. This one here is from Delphine Berset from TÜV Sud. The quote there, using the Trident system for thermal conductivity testing of our process safety studies and related contract testing has provided our lab with invaluable new capabilities with great support from the team at C-Therm. So always nice to hear nice positive reviews there. If you wanted to kind of take a look at some of the other testimonials we do have a quite an extensive list available on our website. Definitely feel free to go check that out. But that finishes up my little introduction here today. I'll be coming back on near the end to close out today's session. But now we're really going to go into the core, call it the meat and potatoes of today's work. And I'll throw it over to you, Dr. Huot, to take it from here. Thank you once again for joining us here today.
Okay, thank you for the introduction. My name is Jacques Huot. I'm a professor at the Department of Biochemistry, Chemistry, Physics, and Forensic Science. It's a long name. And I'm also member of the Hydrogen Research Institute here at the Université du Québec at Trois-Rivières. And my main activities are hydrogen storage and metal hydride. So this is why thermal conductivity is very, very important for us. And this is what I would like to show you today. So I think could go to the next slide. Okay, so the hydrogen economy. So hydrogen is considered to be a good energy vector, especially for the renewable energy like wind or solar, because they are intermittent, so they are not in phase with the utilization. So you have to store this energy in some way, and after that to release it. So hydrogen could be a good way to do that, especially for long-term storage, because if you want, for example, in the north, they could produce, they have energy, for example, with solar panel. This is something that is looking at right now. They could install solar panel, but they could produce energy only during 6 months of the year. So they have to store this energy for a long term. And you could not do that with batteries, so it's better to do that with hydrogen. So hydrogen is, and hydrogen also is used for transporting energy, but also for chemistry. It's used in the steel industry and so on. So it's very important. But if we want to develop this economy, we have to find a way to store hydrogen in a safe way. And storing hydrogen in the solid state, as for example in metal hydride, this is a promising candidate because you have a high volumetric, and the gravimetric is not so good, but high volumetric. So this is an example. For example, if you want to store enough hydrogen to drive a car for 500 kilometers, so you see if you store it in at 200 bar, it's a huge volume. And now they are using 700 bar, so the volume is a little bit is less, but it's still quite big. So these tanks will take a lot of space in your car. But if you use a metal hydride, you could store hydrogen in a much more compact way. And actually, it's a little bit counterintuitive, but you could store hydrogen in a more compact way in metal hydride than in a liquid state. And of course, liquid is high temperature. So if we go to the next slide, so this is a comparison with the different means of storing hydrogen, and you see that if you store at under 1 bar of pressure, then the amount of hydrogen is very small. So you have to go to 700 bar but at 700 bar, 25 degrees C, then your volumetric capacity is not so bad. It's about 1/3 of the liquid, but you have the problem of high pressure. And if you store in liquid, then your volumetric capacity is good. Your gravimetric capacity is also good, but then you have to work at a cryogenic temperature. So this is not very practical for most of application. And you could store it by adsorption. So this is a van der Waals. So, but again, you have to go to very low temperature. But if you store hydrogen for example, in an iron titanium alloy that is used commercially, at 1 bar, you could store a volumetric capacity that is much higher than all the other method and at room temperature. But of course, the disadvantage is that the gravimetric capacity is not so good. So if you go to the next slide, so the advantage of metal hydride is that you have a high volumetric density, you could work at low pressure, and the reaction is endothermic. When the metal is really releasing its hydrogen, it's an endothermic reaction. So it has a benefit for example, if you have an accident and you have a rupture of your tank and there is a fire and your tank is releasing hydrogen, then the tank will cool itself. So the reaction will be killed by itself. So that's an advantage, one of the advantage of metal hydride. But the disadvantage is sometimes it's a temperature of operation. Sometimes if you want to have a hydrogen metal hydride with high capacity, it has to be to high temperature. So this could be a problematic for some application. Sometimes the kinetic is slow. And for the industry, the main thing is cost. Okay, so sometimes with the element and so on, it's a little bit too expensive. And sometimes the powder could be pyrophoric. But still, the industry is looking at metal hydride for many applications. So this is what we will see in the next slide. So you see one of the advantages that metal hydride could be used for a huge range of application. So it could go from portable, like in a cell phone, or a small energy storage, laptop, up to the submarine. And the submarine, it's a real application. Now the German, the Spain, and also Greek Navy, they have fuel cell submarine, and the hydrogen storage is in metal hydride. So that's one of the big advantages of metal hydride, because, for example, if you want to run a smartphone with a fuel cell, it's possible to run a small phone with a micro fuel cell and a small hydrogen reservoir. And actually, you could beat the lithium battery that way. But of course, you could not store hydrogen in a smartphone with a high pressure tank or with liquid nitrogen or liquid hydrogen. So nobody want to have in his pocket something that is minus 250 degrees C. So the only way for this will be metal hydride. So that's another big advantage of metal hydride, is that you have a huge range of application. So next slide. But for the metal hydride, so the absorption is an exothermic reaction, and the desorption is an endothermic reaction. And there is a lot of heat that is involved. So, for example, for magnesium, the heat of transformation is 75 kilojoule per mole. It's very, very high. It's much higher than the latent heat so you need to deal with a lot of heat when you do absorption or desorption. And this is one of the big problem with using metal hydride in a practical application. So for example, if you run if you run the number, if you want to absorb 5 kilograms of hydrogen, this is roughly the amount of hydrogen that you need for a car to get a fuel cell car to have a 500 kilometers range. And if your tank is totally empty and you want to charge it in 6 minutes, so you need to deal with 520 kilowatt of heat that you have to extract. So it's a huge amount. It's a huge amount. So it means that we should have a very high thermal conductivity, because if the thermal conductivity is too low, then it will just kill the reaction, and the kinetic will be much too slow. So that's one of big problem of metal hydride, is to have a high thermal conductivity in your tank. So if we go to the next slide. So these are some type of reactor. So the hydrogen metal hydride tank, and as we saw, you have a lot of heat that you have to extract. So you need heat cooling. Okay, so you have to have some means to extract that heat or to bring that heat, and there are many different ways to do that. So you have to have cooling tube inside your tank, and but the point is that you don't want to have too many cooling tube, because it's added weight and it's more complicated and so on. So you want to reduce the number of cooling tube, but in order to reduce the number of cooling tube, you have to have a relatively good thermal conductivity between these cooling tube. And I spoke with a guy from a company, and they were building the tank, and he said the limiting factor between for the distance between our cooling tube is actually the heat conductivity of the powder itself. So we could not have a cooling tube every 50 centimeter, because the heat will never go through the center, okay? Because the metal hydride itself has not a very good conductivity. So it's very important to measure that heat conductivity of the metal hydride. And if we could measure it well, then under different configuration, because usually, well, a metal hydride, when it absorbs and desorbs, it's swelling up and going down up to 25%. So a metal hydride in the storage tank will always be in a form of powder, always. Okay, so you have powder, so you have the problem of having a powder, and to try to have the best thermal conductivity within this powder. So you could play with that. You could press the powder at different pressure. But then if you press too much, then if it's 100% dense, it's not as good, because hydrogen could not go through. So you have a lot of parameters that you need to play with. But in order to play with these parameters, you have to know what is the thermal conductivity. So this is why. So people are using sometimes expanded graphite that they mix with their metal hydride in order to improve the conductivity. But again, you have to measure these thermal conductivity, and this is not so obvious. So for us, having a good way to measure thermal conductivity is really crucial. And I have the whole project that are just based on measuring the thermal conductivity. So with this, I think I could leave the floor to Genesis. Yeah, thank you very much.
All right. Hello, everyone. Just a quick introduction, I guess. My name is Genesis Infante, and I'm the current lab manager for the TAL Thermal Analysis Lab Group at C-Therm. And I'll be presenting our work in collaboration with Dr. Yu and UQTR in terms of like testing the thermal conductivity of the metal hydrides. So I hope that at this point, everyone has a better understanding of the importance of thermal conductivity with the applications of metal hydrides and how metal hydrides can offer this advantages over different other hydrogen storage systems like gaseous or in a liquid form. And the challenges that are incorporated with that application. How do you test thermal conductivity at this particular conditions? And again, shown in the screen right there. The basic conditions that we're playing around here is that you'll have your metal hydrides in different type of like density quality, and under applying hydrogen into that metal hydride and typically under high pressure and high temperature. Basically, you want to test thermal conductivity with closest to what your target working condition would be. And oftentimes that can be very, very challenging. So us here in C-Therm, we've worked really, really hard on trying to give that capability to anyone that's interested. So just go to the next slide, please. And in addition to the high temperature, the high pressure, and the under hydrogen environment, another important thing to consider is that the actual formatting of the metal hydride species that you'll be testing. So as Jacques said, like it's very important to understand how heat transfers through a loose powder form, or how that changes as you densify those powder. As you can see here, like in a loose powder form, you'll have a significant amount of interstitial air in between the powder particles, and that air or gas, I guess, would be filled up with hydrogen in this case, will have a more significant contribution to the effective thermal conductivity of the system. So, depending on the conditions and the working conditions that you're looking at, you might want to look into like whether you want to apply it a more consolidated form of the powder, so in a pellet form, or in a bulk form. So which is very rarely done, as not all working operating metal hydride storage systems involves bulk forms of these materials. So in us in C-Therm here is that like we can accommodate for any type of that formatting. So when it comes to hydrogen storage application, either you'll have a powder or you'll have a consolidated pellets. So those are the two typical relevant forms that we can play around with. And depending on those form, we can offer two methods to cover like either you use the transient line source, the TLS, when you want to test the powder, and the transient plane source, or the TPS, are more highly recommended for pellets and solids. So like all of these has to be accounted for. In addition, another factor that we have to really think about when it comes to testing metal hydrides is that because of the variability of this reactivity and the species involved, different groups we're working with different types of metal hydrides. We have to think about the chemical robustness of the setup itself. So for example, the TLS needle probe is constructed out of stainless steel. So that it's a really robust system that can handle most tough conditions. But if your species is highly acidic for some reason, it's probably not as recommended in a sense. Stainless steel tends to be very sensitive to acidic conditions, on top of the potential to further be sensitive against hydrogen. The transient plane source, the TPS, is constructed using Kapton-based material. So that's yellow film right there. Kapton by DuPont is typically very robust against most chemicals, except highly basic conditions. So that's something that you have to keep in mind. And we offer other alternatives in case your sample are in that kind of like category where you might need to kind of like adjust accordingly. So starting with our high pressure TPS, the transient plane source, shown right here is the high pressure cells that C-Therms are offering, and next to the Trident platform right there. What's not shown is the TPS sensor previously shown, and how we accommodate for that sample, basically the sample holder and the sensor together. And it's not shown because it's inside the cell right now. What's also shown on this page is the technical specifications for the high pressure TPS. So C-Therm offers this capabilities for pallets. So you'll need at least 2 pieces of pallets as identical as possible. So in terms of density and how you densify them, we preferably you would like that to be as close to as possible. In terms of the atmosphere, it can handle hydrogen, inert gases, air, and vacuum. Sample size would be in the 20 millimeter diameter range. Less if you have less materials to work with, just let us know, and we can try to maybe adjust around that. Typical thickness would be somewhere in the 10 to 15 millimeter for each pellet. And thermal conductivity range would be somewhere in the 0.1 to 50 watts meter Kelvin range. As for operating pressure and temperatures, operating pressure would be up to 140 bar, or about 2000 psi. And for operating temperature, it's -15 to 300 degrees Celsius. So just for everyone that's not very familiar on how the TPS work, the basic principles of operation is that typically the sensor is sandwiched between 2 pieces of the sample. That's why we're requiring you to have two of these pallets, as the TPS method operates under a symmetry kind of assumptions. And the basic premise is that we input a power into this, as the sensor is also the heat source at the same time, and that heat transfers into the sample. We monitor that change of temperature over time, and then from that temperature change over time curve, we can get the thermal conductivity and diffusivity of the material. There is a little bit of operator involvement in between those during those testing, where you have, as the operator, you have to input the power level, you have to input the time, and all that depends on the material type and the sensor size that you're working with. All of that is mentioned under the guidance that we offer, but also under the ISO 22007-2 standard. Yeah, coming back to the high pressure cell right there, shown in this slide is the pressure, on the left is the pressure cell and the associated TPS sensor. And you can see that on the right is the sample holder, where we insert the pallet in there, and you'll have a spring-loaded force basically keeping the pallet pressed into the TPS sensor itself. It's very important that we maintain that compression basically on the stack. So we want to maximize the contact between the samples and the sensor itself. And also, as the cycle between hydrogenation and release of hydrogen, there is an expected change on the pressure itself because of the expansion associated with the material. So as you can see here, there is it's a whole process on how we're gonna set it up. And again, part of the guideline is, this is how you do it, and we offer all that whenever you need it. And if for some reason your requirements are more on the higher pressure range, there are options for 3,000 to all the way up to 5,000 psi options, and we can definitely accommodate that depending on the conditions that you're requiring. On the right is just the top view of what it looks like in terms of the TPS sensor and the sensor stack. So now on to the actual results that we measured using the titanium iron alloy metal hydride that has been provided to us by Jacques and the UQTR team. You can see here is the extensive data that we've measured in different conditions. So we've tested it under vacuum, under air, ambient air, under ambient hydrogen, and under high pressure hydrogen. So starting from step 1 on the line graph right there, the y-axis is the thermal conductivity. We've tested the titanium iron manganese alloy pellets using the setup that we've described the last 5 minutes or so. The first step is that we've removed all the air inside the cell and induced vacuum. Once the vacuum is induced, we've performed the thermal conductivity testing using the TPS method. And you can see that the thermal conductivity is in the sub 1 watts per meter Kelvin. It's about 0.6, I believe. However, when we insert back ambient air into the system after removing air with vacuum at step 2, you can see that the thermal conductivity is now much higher compared to the vacuum state. It's about 1.8, so it's almost triple thermal conductivity. And this comes back to like the importance of the format of the sample that you were testing, and accounting for that interstitial air in between particles whenever you're testing this types of material. And and all these data sets so far are actually a repeated test of at least 3 or 5 data points each. And you can see that it's very tiny probably in your screen, but like the error bar is very tight, and it's a very repeatable process at this point. And speaking of repeatability, we remove the air again and see if we can actually induce the same or measure the same thermal conductivity at step 3, where we vacuum the system out again, removing that air out. And you can see that we were able to repeat that similar value of about 0.6 watts per meter Kelvin. At this point, we've tested about 7 bar hydrogen after removing the air. And the thermal conductivity is much higher in this case. It's about 5.3 watts per meter Kelvin. And that big increase in thermal conductivity can be associated with the hydrogen that are within the pellet itself, but also you could also associate that maybe on the hydrogenated form of the alloy. At this point, we tested like, okay, what if we remove that high pressure and see the effect of the pressure itself? And you can see that at step 5, ambient hydrogen, so basically just one bar inside the cell, you can see that it lowered to about 3 watts per meter Kelvin. Again, testing repeatability, and we can if we can get testing whether we can repeat it, and also confirming that the values that we get are accurate. We repeated the high pressure 100 psi 7 bar hydrogen atmosphere, and you can see that we matched it with our previous measurement. And again, removing that high pressure back to the ambient, and then we matched that again from our previous ambient pressure. At this point, we want to test whether like, oh, all this are like, we want to understand whether it's just the hydrogen or if there's a fundamental change within the pellet itself or the material itself. We removed that hydrogen out by inducing vacuum again, and we were able to repeat that value, the low value of about 0.6 watts per meter Kelvin at the beginning, at the vacuum state. And again, repeatability is always what we're aiming for at this point, whether from vacuum to high pressure. Again, we're able to get that value of about 5.3 watts per meter Kelvin. So obviously, at this point, we'll have like an increasing trend overall as we're playing around with pressure, and that's for the pellet form of the titanium iron alloy. So moving on, the other methods that I mentioned earlier is for the high pressure TLS. This method is for powder form, and or the very, very granular form of the metal hydrides. Again, similar atmosphere, it can tolerate hydrogen and gas. In this case, because we're working with powders, the sample requirements is more about the volume rather than the dimensions, mostly because we want to have the needle to ensure that we have enough material to surround the needle and able to actually measure it in a proper way. Thermal conductivity is between 0.1 to 6 watts per meter Kelvin. And again, the range is typically in a lower side of things, mostly again, because in a loose powder form, you have a lot more interstitial air in between the particles, and that really brings down the overall effective thermal conductivity of the system. Operating pressure is all the way to about 3,000 psi max by default. And operating temperature is minus 55 to 300 degrees Celsius. And basic operation is pretty much the same as the TPS with some slight modifications here and there. But the basic principle is it's pretty much the same. The power input into the needle, and the needle heats up. That heat transfer into your sample, and then we measure it as a change of temperature over time. Slight difference, or the main difference between the two methods so far is that it's a line source versus a planar source, and again, there's a different implications on how the math works and all that, but again, it's fundamentally similar in a way. So shown right here is our TLS high pressure cell on the left. It's about 50 millimeter in length, and again, the minimum volume is usually somewhere in the 60 mil total amounts. And you can see right there is an example of a metal hydride powder inside the cell itself. I believe this is magnesium in this picture. Yeah. So similar tests, or at least sets of tests, has been performed using this time just the powder form of the titanium iron metal hydride. You can see that at the beginning, though, we started measuring it in air. The value that we ended up getting was about 0.21 watts per meter Kelvin. And again, all that is a set of 3 or 5 data sets per condition. We remove the air out of that system, and you can see that it also drastically decreases it. So I believe it's in the 0.0 in a sub 0.1 watts per meter Kelvin value. And having that system vacuumed out repeatedly, we introduced hydrogen in this case in a lower range at 1.4 bar, and it measured to about 1.1 roughly. And again, repeating that measurements over and over again for 3 to 5 times and increasing that pressure. You can see that in this case, there's barely any change in the overall thermal conductivity of the system. And it might be implying that like the hydrogen itself is the major contributor on the that value, or something else is happening that we haven't been accounted for. And again, after inducing the high 6.9 or 7 bar hydrogen, we remove all of that under vacuum, and we're able to repeat the value that we measured at step 2, which is about 0.06, I believe, watts per meter Kelvin. So at this point, we still are like highly like putting a lot of focus and effort into doing more testing under using our high pressure cells in both TLS and TPS methods using Trident. We are still undergoing a lot of like testing with different species, so not from the titanium iron alloys. We're considering other like lanthanum nickel, for example. Again, thanks to Dr. Huot and providing all the samples to us. And we might have to generate more data for future work. And at this point, just all I could say is that stay tuned, and we'll probably give you more data in the next few months or so.
All righty. Thank you to both of our speakers here today. I'm just going to wrap things up here with a little bit of a kind of closing out. I've seen some questions come in for the Q&A. So when we get to the end of this section, we'll jump into the Q&A part. Again, if you've got questions, definitely feel free to type those in, and we'll be addressing those shortly. So, if this webinar was interesting, this will again be available for playback, but we also have all of our webinars that we've put on over the years available on our website. Range of different applications, different methods, different focuses. So you can give that a check out. Again, it's all available for free. We also have a tech library. So many of our presentations will feature data from different academic groups or industry collaborations. They're all also, again, available on our website, or at least the link to where you can find them. Again, I mentioned earlier, but if you did want to learn more, feel free to reach out to us. We do offer technical consultations where, again, we could go a little bit further in specific examples related to what you're working on. You could see a live demonstration of some of these methods and on different samples. So if that's of interest, again, definitely feel free to reach out. Also, if you're just looking for general pricing information, you kind of want to get an understanding of what this type of setup would cost, requesting a quote is quite straightforward. So either options, we're happy to provide assistance there. If you're not already doing so, give us a follow on LinkedIn. This is where we post all of the latest and greatest content, whether it's webinars, blog posts, collaboration pieces. That's going to be where it's going to be set up first. So definitely check that out. And I will mention we do have a couple upcoming webinars. So in February, we have 2 so far. The first one here is actually looking at using transient methods to measure the thermal performance of condoms. Interesting application. We've seen a little bit of an inquiry into that specific space over the last little while. So we thought we'd do a webinar on it. So we'll be talking about condoms as well as just other general thin film characterization approaches. And then later in the month, towards the end there, measuring thermal conductivity on a budget. This will be focusing in on the thermal conductivity kit, or TC kit. This uses the TPS method. There's some differences between the TC kit and obviously the Trident platform and what they provide you. But this is a nice entry-level system, again, if you're just looking to get into this space. So we'll be featuring some specific content on that one. Upcoming events. So we're also going to be, at location at certain events over the next few months. Currently, actually, we are at Nanotech 2025. That's, as I mentioned, currently going on in Tokyo, Japan. if you're in the area, and I think it's going until tomorrow. If you happen to be in the area, definitely feel free to swing by. You can find us there. We do have a booth 5U-02. And then in February, thermal management for EVs and HEVs. This is being held in Munich, Germany. That's February 25th to 28th. And then lastly, later on in March, we will be at PitCon. This is held in Boston, the United States, March 1st to 5th. All right. Once again, thank you for everyone who joined us for today's webinar. I will once again thank both of our presenters, my colleague, Genesis, as well as our special guest speaker, Dr. Jacques Huot from the Université Québec Trois-Rivières. At this point, we will close out the official recording and recorded session here today, but we'll go into the Q&A at this point. So again, if you're interested in sticking around and having a little bit of a discussion there, please feel free to do so. But if you are dropping off, thank you for joining, and see you at the next one.